the area. So
Yes.
it has applications mostly in, for example, what? This is a possible application, but we may use it for what? To analyze the shape, like.
Leaf, for example. They use for leaves. And
Mhm.
also I don't know how to say in English, but delikli kumaşlar için üretilen makinelerde
Yeah, for
kullanılıyor.
image processing, you mean?
Yes, for image processing.
For image processing, you want to make
Yes.
some processing for a certain object. So first you recognize the object, and then you find its convex hull. So
Yes.
you get rid of the remaining parts of the picture so that you can focus on, that's what you mean by analyzing, on what is in the convex hull, do some processing, filtering, whatever you want to do. So that would make your life much easier and increase the quality.
Yes,
Sure. Yes, that's a very,
we find
yes,
the
that's a very
outermost points.
points. Yes, that's the convex hull, to find the convex hull. That's a very good example. Another other thoughts? Are there other thoughts from the audience?
I think we can use them for self-driving cars,
Yes.
for
How?
collision detection. If we think the car itself as a convex shape, we can calculate their collision area easier.
Mm-hmm. Mm-hmm. I mean, the car has a shape, you mean, and you can
Yes.
find its convex hull, okay?
Mm-hmm.
And then it
That
would be much easier to determine its distance to the other
other
cars,
shapes
right?
around. Yes. Yes.
Yes, that's also another good example, which I didn't have, by the way. The first one, more or less similar, I had, but this one is new. And maybe I need to, okay, I will write them down now. Just a minute, let me. Okay. So you see the, I don't want to see this. I don't know how to get rid of this. Anyway. So you see OneNote, right? I shared my screen. Do you see it?
Yes, we can see. So.
Okay. So let's talk about some applications, some possible applications. Convex hulls provide of object shapes and data sets given. Let me give it to you as an example here. This is similar to the example that your friend has given, but for computer animation. But for self-driving cars, it's an even better example. More or less the same thing. We replace them by their convex hulls, so we can find we can detect the collisions more easily. So another example that you haven't talked about is in statistics. Detecting outliers by some statistical techniques. Let's say that you have a certain set of data like this as points and some others, and you want to find the area where most of the data is, in which case here, for example, and you determined that and you want to detect the remaining are outliers. So does anybody, maybe some of you have used Microsoft Office Visio, for instance, finding bounding boxes. For example, bounding boxes. They are called bounding boxes in MS Office Visio. In some computer programs, for instance, you have a picture, you save it in Visio or whatever, and that may be some picture, but it's too big in the entire frame, okay? It's too big, some picture like that in the entire frame. Just a minute. So, but you don't want that. Then you find a bounding box and save this part so that in the remaining, when you save it, you end up with this file, okay? Just that portion. So visual pattern matching in image processing also, for example, in detecting license plates. So you know that the license number is somewhere there. That's the plate, but you want to focus more on it. So you find its bounding box and then apply some image processing techniques to actually read what's there. So that's for the applications. Now we will continue with the theoretical part. Theorem. The convex hull of any set S of any 2 points is of any set of any set S of n greater than 2 points, not all on the same line. So we don't want all of them to be in the same line. 2 of them might be on, I mean, they constitute one, but not all on the same line, is a convex polygon with the vertices at some of the points of S, okay? With the vertices at some of the points of S. So we call these them extreme points. We need to find the points that will serve as the extreme points. So what do I mean by this visually? I have a set of points, not all of them are on the same line. So if they are on the same line, then it doesn't matter, okay? There is just some line. I don't want that. I will select a subset of these points, which are called extreme points, and they determine the boundary of this region. Okay. For example, here, do you think this is one of the extreme points? Can I take it as a vertex of the polygon that constitutes the convex hull of this region?
I think not.
Not, because if we have it like this, something like this, then we would have to do something like this. Then it would be concave. It would not be convex. So this we cannot take. But I think this we can take, and this we can take, right? Probably this also. The remainings we need to analyze, okay? If it were a more if my shape is like this, for example, my points are like this. Sorry, let's constitute. Okay. Then I would, if I take these ones, not the ones inside, then definitely I can say that these constitute the convex hull. Okay. Like this. So, so which of these points are the extreme points? That's the question, actually, because once I determine the extreme points, then I can connect them by lines and find the convex polygon that constitutes the convex hull of a set of these points. Is it clear?
Yes.
Okay. So we also need to know which pairs of points need to be connected to form the boundary of the convex hull. And okay, once we find the extreme points, we need to find the sequence of these points so that in the clockwise or counterclockwise direction, if I go in that direction, then I can draw the convex hull or determine the convex hull to the computer, in other words, okay? And not only the points, but an ordering of the points such that when lines are drawn between these points in the clockwise or counterclockwise order, it doesn't matter because it's a polygon. Then I can find the shape, okay? We need to find the points that will serve as extreme points. So a formal definition of extreme points. Extreme point of a convex set. Okay, before giving the formal definition, I will give the formal definition. What do you think the formal definition might be? If somebody asked you, I mean, not the computer, you, to find these extreme points, you say them by looking at the figure, right? The shape, but what does your brain do actually to determine them? How do you actually determine it? Or I mean, that's the same question as how do you tell a computer to determine the extreme points? What are their properties? For example, we said that the ones here in the middle are not extreme points, or here, for example, we said that this is not an extreme point. But why do we say that? Assume that it's an extreme point, then what would happen? What's the nature of this point? You can think about it. It's not a very easy question that you can answer immediately. You can think about it like 30 seconds or 1 minute, whatever.
Maybe some method like we should check if it's on the edge or not.
Can you repeat the beginning especially? Maybe?
I'm not sure, but maybe we can try to detect that the point is on the edge or not.
On the edge, you mean, what do you mean by the edge? We have a points now. We don't have edges yet.
I mean, something like if we have a matrix or something like that, if we
Mhm.
find a set of data that we have, maybe we can try to find properties of edges.
You are close, but it's wrong in how you express it. But you have a point there. Like you actually are about to find the correct answer, although the current answer is not correct. Think about the definitions of convex and concave. In the convex, for instance, we said that this shape is not.
Screen is gone.
Yes. I'm listening.
Your
Yes.
screen is gone.
My voice is gone.
No, sorry. Your shared screen.
My shared screen. Okay.
Can
Now
we
you
do
see it, I
that?
think.
Can we put a point center of the shape and then calculate the whole differences between distance between any points?
Here we said that it's concave because if I draw a line here, okay, some part of it is there, some part is inside, okay? If I take just 2 points in this region, it goes out of this region, okay? So that's why these points, I shouldn't take this point, but these ones I take. So in these corners, which are the extreme points, if I take, take a convex set of points, okay? If you draw one line between any two of them, so let's say these are the points you take. If you draw a line between any two of them, like here, for instance, then the remaining points, all the remaining points are on the same side, okay? Not the other side. But for instance, if I had taken this point also as one of the extreme points together with the others, then if I had taken this point and some other point, for example, this line, okay? I mean, think of this as an infinite line. Some points would be in this region, some points would be in that region. So I want them to be all on the same side of the line. If I draw a line, okay, I need to pick my points in such a way so that I can ensure that the region defined by these extreme points is a convex region, okay? So you are close to the answer, but not just as formal as it should be. Of a convex set is a point of this set that is not a middle point of any line segment with endpoints in the set. We also need to know which pairs of points need to be connected. Just a minute. So, which pairs, you still see the screen? Do you still see the screen?
Yes, we can see it.
Okay. That is not a middle point of any line segment with endpoints in the set, okay? So we also need to know which pairs of points need to be connected to form the boundary of the convex hull? Because I cannot connect just any two points. For example, here, we can say that, for instance, these are the extreme points. This, okay? But for instance, if I connect these 2 points, I can say with confidence that all the remaining points are on the same side, right? Because we don't have anything here. All of them are here. But if I connect these two, they are still both extreme points, but some of them are here, some of them are there. So I cannot say this for any two pairs. I also need to find which of them I should connect, which means that I need to find an ordering, okay? We can address this issue anyway. We can address this issue by listing the extreme points in a clockwise or counterclockwise order. Okay. So how can we solve this problem in a brute force manner? Like finding the set of extreme points. So let me write the observation that we thought of. For some reason, I can't find the blue color. I can't, so I don't know. Okay, now I did. So observation, a line segment connecting 2 points Pi and Pj of a set of endpoints is a part of the convex hull's boundary if and only if all the other points of the set lie on the same side of the straight line. Through these points. Assume here that no 3 points of a given set lie on the same line. Okay? So how can you solve it in a brute force manner? Like you have points like these. So this is fine, for instance, but this is not fine. So
we
you have a set
check
of
all possible lines.
all possible lines, meaning
Yes.
what constitutes a line? The starting and ending points, right? Which are like
Yes.
2 points. So we can check all pairs actually. For instance, we check this and this, for example. Can both of them be on this on the constitutive convex hull? Then yeah, can both of them be extreme points? No, because if I do this, not all of them are on the same line. Okay, not all the points are on the same line, so I eliminate that. But instead of that, if I had picked like this and this, then I would draw a line and check that all the remaining are there. So good that this is the answer. So what do you think the complexity would be?
N square.
Why do you think it's n square?
For 1 point, we need to compare n minus 1 points. And
But
need
we
to
don't
select for-
compare it with 1 point. We check all of these pairs. We check all points of size 2.
Then we use combination.
Yes. So how many pairs are there?
Hocam n'in ikili kombinasyonu nasıl söyleniyor?
Okay, and choose 2. And choose 2.
And choose
So, okay, once I determine which points, for instance, here, let's assume that these are these 2 green points, then what do I do? So definitely I have an n choose 2 component, okay, because there are n choose 2 number of pairs. But for each specific pair, what is the complexity of the operation that I do? I check all the remaining points, right? That's what you said. So how many remaining points are there? N minus 2, right? So I check whether all of these n minus 2 points lie on the same side of the line. Okay? So that has an n minus 2 component also here, which makes the total complexity n cube as opposed to n square. There are n square number of operations, but each operation takes linear time, not constant time in this case. Okay? So let me write the algorithm first. Not as a pseudocode, but repeating this test for every pair of points yields a list of line segments that make up the convex hull's boundary. Okay. What is the efficiency of this algorithm? So for each of n choose 2, which is equal to n minus 1 over 2 pairs of distinct points, we need to check whether are on the same side. So this makes n cube complexity. Okay. So now I will give a formal definition of exhaustive search, and then I will talk about the traveling salesman problem, which is very famous in computer science, and you may have also heard about it in your programming classes. So that was the exhaustive search approach to the convex hull problem. Okay, check all pairs, but now for each pair I have a linear operation which makes the complexity n cube. Combinatorial problems. Deal with combinatorial objects such as permutations, combinations, and subsets of a given set. Many of them are optimization problems. Exhaustive search is simply a brute force approach. I will abbreviate it as ES to combinatorial problems. It's just generating each and every element of the problem domain. Okay. So let's talk about the traveling salesman problem. Okay. So in traveling salesman problem, we have a set of cities. Okay. And the salesman wants to travel all the cities, starts from a particular location, travel all the cities and come back to the original location. And we don't want to visit one city more than once. Okay, we want to visit them exactly once, but we want to find the order of these visits. And you can think of them as okay, not, but as a graph is more convenient. Okay. And like there's a distance to go from one city to another city. Okay. And if this city I, city j is, this is cost ij. So there's a cost associated with city I and city j. And let's say this is vertex I and vertex j, and there's a cost associated with this edge. So I want to go like, for example, maybe this order, maybe. But another possibility is to go like this way. Sorry. Like this way, maybe, and then this, and then maybe this. We don't know in each of them it's a cycle, but we want the total cost of the edges to be minimum. Okay, we want to find the cycle that gives the minimum total cost. Actually, we are actually given, I can go from one city to any city at any time. Okay, so that means that I'm actually given, it's called, for example, with 4 cities or 4 vertices in a graph, I would say. So these vertices represent cities, and there are possible points. You can go from anywhere, from one vertex to any other vertex, okay? And there's a cost associated with them, BI, VJ, CIJ. So how do you find the cycle? Maybe you could go like this, okay? The green one, or you could go like this, for example, another. So which of these 2 options, for example, you select? Find the mean cost cycle, okay? To find the shortest mean cost tour, meaning a cycle, through a given set of cities, that visits each city exactly once and returns to the original city. So this is actually called a Hamiltonian cycle, this kind of a cycle that visits every node is called a Hamiltonian cycle. Input is a complete graph. Okay. And TSP, traveling salesman problem, is to find a mean cost Hamiltonian cycle in a complete graph, more formally, okay? In a complete and edge-weighted graph, of course, edge-weighted. We are given weights or costs to the edges, okay? So can you think of an exhaustive search approach? An exhaustive search approach to TSP. You think about it, and I will connect my tablet to the charger, okay? In the meantime, you think about it, what? So, okay, what do you think? an exhaustive search approach is? Any guesses? Can you hear me?
Yes.
What can be, you don't need to have to talk about in terms of Hamiltonian cycles, or you can explain it in your own terms. You are given a complete graph. So meaning that everybody is connected to everybody. That's what the complete graph is. It would be too complicated here, so I cannot maybe draw all of them, but that's what it is. And there is a weight cost on all of these edges. And I want to find the cycle that passes through every vertex exactly once, of course, otherwise it wouldn't be a cycle. And the total weight is minimum. And I am trying to do it in an exhaustive search way. Because I'm trying to find a cycle, and every cycle has a total edge cost, right? So I can find all the cycles, enumerate them, enumerate all the cycles, which are called Hamiltonian cycles in this context, enumerate them, compute their total edge cost for each of them, and pick the one that has the minimum total edge cost, right? So once I have all the cycles, then it's straightforward because I can simply compute them by summing up all of their edge costs, and finding the minimum is also easy, okay? The difficult part is to enumerate all of them. That would be the exhaustive search approach because I check each and every candidate solution. Candidate here meaning Hamiltonian cycles, okay? All of the cycles that passes through all of these points, all of different cycles. So an exhaustive search approach to TSP is generate all Hamiltonian cycles and choose the one with total minimum total cost, or mean cost for short. Okay. A Hamiltonian cycle can also be defined as a sequence of n+1 adjacent vertices, and I will explain why. Like VI0, I0, VI1, VI n-1, and then VI0 again, where the first and the last are the same. The first and the last are the same because it's a cycle. I need to turn back to my original starting point. So that's why the first and the last are the same. And that's why I explain it with n+1 adjacent terms, because I need to pinpoint which one is the starting and also at the same time the ending point. Okay. So this is, we can get these tours, okay? So we can get all these tours. How can we generate them? It's like I have cities, okay? And there's one possible way of going this, another possible, it's like I have people. How can I, and I have a round table in a circular shape. And in how many different ways can they sit around this table? How many number of seating arrangements are there, right? Or something different? For example, I will explain in an example. I think our time is up by it. Anyway, think about this example, okay? Because you are also responsible from this in the exam. You can find the answer from the internet, but think about this. How many possible cycles are there? One possible cycle is this, right? A, B, C, D, A. And another is this. A, C, B, D, A. Or A, B, C, D, A and A, D, C, B, A. Are they two different cycles? A, B, C, D, A and A, D, C, B, A. Are they two different cycles?
They are same.
They are the same cycle, right? Because going from telling them in the clockwise direction or counterclockwise direction doesn't matter. So it's like I look at it from this point or from the other point, then it shouldn't matter. So is it really like the seating arrangements on a circular table around the circular table or something else? A ring maybe. I have a ring and I have these small things, I don't know, boncuk, something like that. And I want them on this circular ring, but whichever way I look from it, it doesn't matter, okay? So I need to actually divide it by 2. If it were just the cycle, like these seating arrangements, and then it would be generating all permutations of these n-1 intermediate cities, right? Because I fix the start and end as A. I mean, I may fix it with others. I could explain it in terms of B, C, D, A, B also. That would also be the same cycle, right? B, C, D, A, B. It doesn't matter. So there are n-1 factorial options, but because these both cycles in the if I read them in both directions, because it's the same cycle, then I need to divide it by 2 also. Okay, so we can get all tours by generating all permutations of n-1 intermediate cities. Divided by 2. And this division by 2 is because of the reason that I just explained. So that actually becomes n-1 factorial over 2. There are n-1 factorial over 2 possible of candidates. So for instance, here with 4 and 4, I have like 4 minus 1 factorial over 2, which is 3 times 2 over 2, which is 3 possibilities. There are 3 possible cycles, enumerations, okay? So, and these are like A, B, C, D, A, C, B, D, A, and A, D, B, C, A, I think. A, D, B, C, A, I think, okay? So I need to enumerate all of them, but just keep in mind, I mean, that if I enumerate, I have factorial. So it's a lot of complexity. exponential complexity and a huge exponential, which is factorial. Okay, so our time is up, and even 4 minutes more, and you're responsible until the end of the traveling salesman problem in this exhaustive search section. We didn't start the knapsack problem yet. We will continue it 2 weeks later after next Thursday in the same class hour after your exam, and your exam will take place next week Wednesday. You already know it, but I would like to remind you that the classrooms and seating arrangements will be, I mean, not the arrangements explicitly, but the classrooms will be announced on Teams, and you can also find them when you come to the exam also. I mean, it will be exactly as it used to be before the pandemic. The same, I mean, already in class you have the same seating arrangements, so there's nothing in particular that you need to pay attention to. Good luck in your exam. Okay, bye guys. Class is over.
See you, sir.